Yeah. You'll zoom out a little bit. First of all, my apology. I don't know what Hilbert Space is. As I should warn you guys, I was raised by physicists, and sometimes it shows because like whenever we talk about Hilbert spaces in physics, it's always in the context of quantum mechanics, which is in the context of complex inner product space. But that's just an artifact of my education. The real Hilbert space is just a real or complex inner product space that is also a complete metric space. So to say it's a Hilbert space, to say it's an inner product space, which is also complete. A Banach space, on the other hand, is just, it's got a norm and it's complete. But there's no inner product in a Banach space. So now I got that out of the way. Let me talk about what you're actually interested in. The Afterparty. Let's see here. So yes, true. It is in fact true that if the rank is 13 and the dimension of V is 42, because what does that mean? Well, rank nullity tells me that the nullity, which is the dimension of the kernel, is what? 29, which means that there are lots of eigenvectors with eigenvalue 0. In fact, I didn't need so many, but just to make sure you didn't start writing down a matrix or something, I made the numbers big. Anyway, it is possible for a 3 by 3 matrix to have no eigenvectors. No, it's not possible, because the characteristic polynomial is a cubic equation, and any cubic equation with real coefficients has at least one real root. By the intermediate value theorem, right? It has to cross from positive to negative or negative to positive. So somewhere there's a real root. It may or may not have a complex eigenvector, right? Well, depends on how you think about things. It may or may not have a genuinely complex eigenvector, let's say, but definitely always has a real eigenvector. Yeah. Well, anyway, problem 2. Here's how I looked at it. You might have looked at it a different way because you didn't know what it was from the start. But basically the point of this hint is that if you look at lambda equals to 1, that would be saying that 2a plus a transpose is equal to a again, right? Which translates into a transpose equals to minus a. So eigenvectors with eigenvalue minus 1 are antisymmetric matrices. And if you set this equal to 3a, you get the condition a transpose equals to a. So both symmetric and antisymmetric matrices form eigenvectors for this linear transformation. But we've worked this out before. We know that the direct sum of symmetric and antisymmetric matrices gives us all of our n by n. So I go through the argument here, right? Here's how to prove it's a sum, because you can add this plus that, and you get any a decomposes like this and that. That is symmetric, that is antisymmetric. So this shows that the sum of symmetric and antisymmetrics is the whole deal. And also if you look at something in the intersection, well then you got a equals to minus a, which means that a is equal to 0. Consequently, n by n matrices are the direct sum of symmetric and antisymmetric. We've gone through this before. If you said that on your quiz and didn't work all this out, I was fine. I'm including it here so you know the details. So if I wanted the details and asked you for details, you could supply them, yeah? Anyway, and then I proved down here, of course, what I just said already, which is that if we feed an antisymmetric matrix, a symmetric matrix, did I reverse the order of them? I may have set it opposite. I'm sorry, this is, well, it doesn't matter. Anyway, this is the lambda equals 3 space, and that's the lambda. W2 is actually the lambda equals 1 space. Oh, here it is anyway. W1 is the eigen 3 space, and W2 is the eigen 1 space, as these calculations show. And consequently, we already showed that those are the direct sum of the whole thing, so we're done. And that's kind of neat, because if you look at that, we never even calculated the characteristic polynomial. And I'm glad we didn't have to, because if we did, it would have been this. Oh. Lambda, this many. I mean, it's by the way, it's clearly diagonalizable, because you can see here that if you were to look at a matrix which respected the decomposition, you'd have like 3i blocked with an i for the matrix of it. So it's diagonalizable. Here's the characteristic polynomial for what it's worth. Obviously, if you tried to calculate that directly, you probably couldn't do it, right? This problem 3, you guys had complained to me that there were no adjoints, so I thought, how can I test adjoints without getting super technical? I thought, I'll just ask them for the definition. So there it is. Now there are 2 ways you could have gone. Assuming you got an orthonormal basis, write down my definition. Or you could have written down this condition, which I'd also take as a definition, because it is logically equivalent. And as I mentioned, is the definition in many books. So you could have gone, you kind of go with this, or you could go with that. Either way, I'd be copacetic. And then finally, problem 4. got your 1, your sine x, your 2, cosine 2x. That's clearly a basis for v. I guess it's not entirely clear. You got to prove that sine and cosine in this are linearly independent, but in fact they are. And in any event, you can calculate t acting on these three vectors. So differentiating of 1 gives me 0, so this gives me 1 again. If I feed sine of 2x into the d squared plus 1 map, I get second derivative of sine plus sine again. This gives me a minus 4 plus 1 is minus 3. And likewise, when I feed cosine to this map, this transformation, I get minus 4 plus 1, which is minus 3. So both cosine and sine are eigenvectors with eigenvalue minus 3. And 1 is an eigenvector with eigenvalue 1 with respect to this mapping. So the matrix is that with respect to the basis, which is essentially given, right? And so is it diagonalizable? Yes, we just did that. So, yep. And what is the eigenspaces? This is eigen 1 space, and there's the eigen minus 3 space. That's pretty much it. Any questions? Any questions about the test? We can talk about that too. We got a couple minutes here, if you want. I cancel calculus. I'm fresh out of calculus 3 to teach them. Yeah. Oh, well, the final is comprehensive. So what I do is I look back at tests 1, 2, and 3, and I try to think about what would be, what should students have learned in the process of taking these tests and, doing the homework, and try to go from there. So I would probably start with the tests and kind of branch out from there if I were you guys. Let's see here. I mean, it's certainly possible that some things weren't on the test could be on the final. For example, it wouldn't be terribly surprising if I asked least squares. That's something that is pretty easy that we touched on that, wouldn't kill most of you if I did it, even though it wasn't on a test. It was in the homework, the first question on this test 3 was not supposed to be a trouble, but it was a trouble to many of you, and that was disappointing to me because I was not trying to be mean there, and yet bad things happened. Like so many bad things with this one. I don't know why, but anyway, it's probably my fault. And then this one, some of those of you who got it really, really got it, and those of you who didn't really, really didn't. So I don't know. It's kind of in between. Not a lot of in between here. I will say this: of those who got it, a lot of you lost 1 point. I just took off 1 point because really, really, you should say somewhere, x is non-zero. That's a very important part of being an eigenvector, right? If we drop that, a lot of the stuff we say falls down. Yeah. Is every vector an eigenspace an eigenvector? The answer is no. Eigenspaces are subspaces. There's one vector in there which is not an eigenvector, namely the 0 vector. And I'm sorry about the 6. See, the reason there was V1 through V6 here is I had an uglier 6x6 problem, and then I scaled it back. But in the craziness of preparing the test for you guys, I forgot to reduce my list, and thus the confusion. So with that in mind, I am less annoyed that I saw people write 6x6. I like it. It makes more sense to me now that happened. I understand why you might have done that, even though I still think it's wrong. But I see why you did what you did in light of that. But anyway, with the 40 extra points you just earned, everyone should be happy. No? No, not 40? Oh, okay. Hey, a lot of people got problem 4 right, which was pleasant. Problem 4 is something that I did in class in all of about 2 minutes. But a lot of you had that. That was good. A lot of you got problem 5. Problem 5 was pretty good on the average. Most of you got problem 5. Many of you got problem 5. Problem 6, I'm trying to remember. A lot of you got problem 6 pretty well. I was happy with problem 6, generally speaking. Not too many people got part D. Yeah. But whatever. Let's see here. What else do I have to say? This is a pretty standard linear independence. Problem 7 is like a pretty standard test question. I did work that out in class, but I understand if you didn't. I mean, if you don't have this idea of either going for contradiction or multiplying by t minus alpha, it's really hard to proceed logically there. I mean, if you don't have that idea, I know it's kind of it'll just stop you dead in your tracks. And the trouble with this being inner product is that it's not symmetric. So you guys have said a lot of different, like a lot of people said, well, that's not the inner product in R2. Well, There are a lot of different inner products in R2. Is unfortunate. I should have emphasized that more. I'm sorry that didn't happen in our course. There's all kinds of weirdo inner products on R2. But this is not one of them, because if you look at it, for example, this choice of x and y gives you an example of a fall from symmetry. And then the point of part B was this condition gives you that t is orthogonal. If t is orthogonal, that means that it satisfies the condition that the determinant of t is plus or minus 1. We had a number of homeworks which danced around this idea that was kind of central to about 4 homeworks you guys did, or maybe didn't do, which is understandable. But still, the determinant of an orthogonal transformation is plus or minus 1. So there's no earthly way you could have eigenvalues 1 and 2, because then that would force at least powers of these products, like 1 to the p times 2 to the p for some powers would be in the determinant. There's no way you can have 1 to some power times 2 to some power equal to plus or minus 1. Just can't do it, right? And you know what? A lot of you guys got problem 10. Like, problem 10 is kind of beastly, but a lot of you kind of found your way to it. A lot of you forgot to normalize this thing. Like, great, that's a vector, but that's not normalized. So then you have to calculate its squared length and then multiply by the square root of that. And there's the normalized one of those, and it goes from there. But that aside, there was some pretty good evidence of studying on problem 10. I was generally pleased. So I don't know. I just think you guys took a lot of hits a lot of different places. Those of you who had low scores, it wasn't really one thing. It was kind of a series of body blows, right? Maybe a headshot or two. I don't know. Sorry, too morose. There's still hope. There's the final. Do not give up. Thanks, guys. You can hit it, Liam. Thanks.